Good morning. In my last class, we learned S order correction to nth energy level given by equation 1, and then from this, using this equation, we can calculate the nth level energy En. So this one. Today we calculate these two equations from another viewpoint. We first use about the Taylor series of some functions fx. Taylor series expansion of some function fx where x takes this value del x. Now del x is equal to x minus x0, which is h. When h tends to 0, then we can expand fx around the point x0 like this one. C0 plus C1 x minus x0 plus C2 x minus x0 square like this one. And the coefficients C0, C1, C2 can be determined by differentiating fx with respect to x to different orders, and using these values of C0, C1, C2, etc., these coefficients, we can write fx as like this: fx0 plus f prime x by 1 factorial x minus x0 plus f double prime x0 by 2 factorial x minus x0 square, and so on. So in summation, I can write this type fn x0. So I write fs by s factorial x minus x0 to the power s tends starting from 0 to infinity, where fs x0 is at x equal to x0. So now we can substitute f in this equation. Now we can substitute f by wn by en and del x by lambda. Okay. So then En, so I write here, this is expressions of fx So I can write here if s equal to 0 to infinity w enx by s factorial lambda to the power s. Okay, so I substitute this. X, so I write d s w n n by d lambda to the power s. So en is like this, so I can write to the power this lambda to the power s en s is equal to 0 to infinity. So if I take the different values of s, then I can write en 0 plus lambda en 1 plus lambda square en 2 like this, where en 1 can be written as den by d lambda, en 2 is 1 by 2 factorial d lambda, d2 d lambda 2. So this is first order correction to energy. To En. Similarly, this gives second order correction to En. So this equation we used before as assumptions. Assumption 6. So similarly, we can get the expressions for psi n. Similarly, we can get the expressions for psi n. So psi n similarly you can write psi n as 1 by s factorial s order differential of psi n with respect to lambda and then lambda to the power s. So similarly I can write this one lambda to the power s psi n s, where psi n s gives the s order correction to psi n. So I can expand s equal to 0 to infinity. So I can expand this one psi n 0 plus lambda psi n 1 plus lambda square psi n 2 and similarly. So these two expressions, this was for nth level and this gives the nth order correction. This gives this, so I can write this one psi n 0 plus del psi n. So this part is del psi n. Del psi n gives the correction due to perturbation to nth energy level and psi n 0 is the zeroth order wave function. So these two expressions I calculate just before. So using these expressions, we now calculate these two expressions. Now let us take a Hamiltonian H, whose solutions are not known to us. So we can subdivide this Hamiltonian H into two parts, H0 plus H prime. So H prime is perturbed Hamiltonian and H0 is unperturbed Hamiltonian, whose solutions are known to us. That means H0 operating on some psi n0 is equal to En0 psi n0. So En0 is the unperturbed energy eigenvalues and psi n0 is unperturbed wave functions of unperturbed Hamiltonian H0. And H psi n En psi n. So En, and our aim is to calculate En and psi n. So I use this. So I can write this expression H0 plus lambda H prime, and I use the expressions of psi n in terms of corrections to psi n0. So I can use psi n0 plus lambda psi n1 plus lambda square psi n2 and so on equal to. Similarly, I can use these expressions, corrected wave functions, corrected energies. And then psi n. Okay, so I derive these expressions. So I can write these expressions as like this: H0 psi n0 plus lambda H0 psi n1 plus H prime psi n0 plus, similarly I take lambda square as coefficient. So lambda square comes from H0 psi n2 plus next lambda square comes from H prime psi n1 from this 2 part, so plus, and then from right side I write n0 psi n0 then comes to the lambda part, so lambda part comes from n0 psi n1 next lambda part comes from en1 psi n0 these two only plus lambda square part, so lambda square part comes from n0 psi n2 plus en1 psi n1 plus en2 psi n0 and so on. So now equating the coefficients of lambda 0, lambda 1, lambda 2 square, etc. from both sides, I get h0 psi n0 for lambda to the power 0 part, so I get h0 psi n0 is equal to en0 from lambda to the power 1, I get h0 psi n1 plus h prime psi n0 from right side I get this psi n1 en1 similarly from the lambda square part we get h0 h prime from there two parts, so I get en0 psi n2 plus en1 plus en2 and so on. So I can rewrite these expressions in more handy way. So we can derive these three expressions or S equations in more handy way. So I can write for lambda 0 h0 minus en0 equal to 0. Lambda to the power 1, I take this one, so H0 N0 H0, so this takes H0 En1, okay, then En1 psi n0 minus H prime psi n0 similarly from lambda square I get H0 lambda 2 psi n2, so psi n2 n0 and there should be 3 terms on left side, so I can rearrange this one n0 plus n1 say n1 minus H prime psi n1 so similarly like this if I proceed to this one, then I can write H0 n0 psi ns equal to so I can write psi ns en0. So I take this part, so I write this one en1 H prime, so psi n is minus 1 plus en2 psi n is minus 2 plus ens psi n0 2. So I write this one, this is okay, and en1 psi n1 en2, so I think something like this from this equation lambda square, so I check it's H0 psi n2 and en0 psi n2, this is okay. Then I write en1, oh sorry, I can write this equation, I think it will be better if I write this. So psi n1 and en1, so I write this one, en1 minus h prime, then psi n1, okay, then so I take this one, and so this part is only one here, so I write en2 psi n0, okay, so this is fine. So this gives this part is, this gives the unperturbed solution, unperturbed equation, and others gives the equations for different order of perturbation. So there is an interesting property in these equations. We will see that if we substitute, say here, psi ns by psi ns plus as psi n0, we will see that left hand side of all these equations remain unchanged. So note the interesting property. If we replace psi ns by lambda s equation, remain unchanged. So you see H0 minus En0 you under replacement H0 then it becomes H0 so you come this one, so I can write here H0 plus, and this part is 0 from the unperturbed solution, so I can get only this part. So you see that H0 minus En0 operating on psi n s remain unchanged due to the replacement of the psi ns by this equation, and as here is any arbitrary constant. So we can remove this arbitrariness of this expression psi ns by considering assumption 7. So we can remove this arbitrariness in the expressions of psi ns. Psi ns is the s order correction to the nth level wave functions. So to remove the uncertainty, to remove the arbitrariness in the expressions of psi n s, we use assumptions which states that all corrections to psi n0 are orthogonal to psi n0 itself. That is, psi n0 del psi n is 0. That is, since del psi n can be expressed as the linear sum of all lambda psi n s, so I can write psi n0 psi n s is equal to 0, since del psi n is linear sum of lambda to the power x psi n s is equal to 1 to. So these expressions, can we express these expressions if we write psi n0, and if this is psi n, then I represent this psi n0 by this vector, and then psi n by this vector in this diagram. Then this is del psi n. So from this expression, we can tell that since this is orthogonal, so I can tell that del psi n has no component along psi n0. That means, so from these expressions I can write that del psi n has no component along eigenvector psi n0 or vice versa. That means I can express del psi n as like this. Where k not equal to n. So this is the origin of this expression. This in the first, this is this assumptions number 4, which I stated before. Assumptions number 4 in our mathematical model. So this is the main logic behind why the corrections to nth level has no component coming from itself. It has only components coming from other levels. Okay. So this is the main physical origin of our expressions. So how we use this arbitrary these assumptions to remove this arbitrariness? I can check. I can check. So I write psi n s to psi n s plus a s psi n 0. So I write this one psi n s plus a s. Okay, so despite according to our assumptions, psi n 0 and psi n s are orthonormal, so this part is cancelled out. So we are only left with the expressions. So expressions or wave function psi n s. Okay, based on these assumptions, now we proceed further. Now we repeat equations for lambda to the power s. So take lambda to the power s, then I can write again, repeat here, h0 Now we multiply both sides by brass in 0. On both sides. So from left hand side I get so I can write minus ing E0 plus and this part is 0 for our assumptions 4, and this part, since H0 is Hermitian, so I can rewrite these equations as H0 psi n0, and this part is actually gives you n0 psi n0, and so this part is 0. So left hand side of this expressions is actually 0. So I can write these expressions as 0. Now from the right hand side, what we get? So from right hand side, I can write this one plus n2 So this part is 1, this part is 0, and in between all parts gives you 0. So I are left with only, and also from this part en1 this gives 0. So from this part this comes 0. So you are only left with this. So from this all I get psi n0 h prime psi n s minus 1. So here, and this is ENS ENS oh sorry, this is plus ENS. So equating with this with left hand side, so this is from right hand side. Okay, so I write here equal. So this is right hand side and left hand side is 0. So equating both sides, I get ENS is equal to psi n0 h prime. So finally we get the best order correction to nth energy level due to H prime. So I repeat like this: ENS is psi n0 H prime. So this gives the S order correction to nth energy level due to perturbation H prime. So if S equal to 1, then we can get first order correction. So this gives first order correction to nth energy level. If we write S equal to 2, then it gives the second order correction, and so on. So I can write this one in H prime n, or this gives H prime n. So this gives diagonal elements of H prime or expectation value of H prime when the system is in unperturbed level n. Psi n 0. So when H prime is perturbation is small, then the energy corrections when perturbation H prime perturbation is small, energy shift or energy correction is very small, that is H prime in n tends to 0, and in that case we proceed to calculate, and then we proceed to calculate second order correction to nth energy level. To the nth energy level, that is N2. That is N2. So when H prime is small, to get any corrections to nth energy level, we then proceed to psi n2, and for then psi n2 can be determined when s equal to 2. So to get En2, second order corrections, I use this equation. Psi n2. Okay, so to get second order corrections, I have to calculate psi n1. So next day our aim is to calculate psi n1, that is the first order correction to nth energy level when the system is in the nth state, and after getting psi n1 we can determine so En2. So in our next day I determine psi n1, and then we proceed to En2. Thank you.